Okay, so hello everybody, my name is Luca Brelli, I'm a PhD student in the University of University of Turin, under the supervision of Federico Bruzia from the University of Turin and Nicola Maia Pugno from the University of Trento. So, quick outline. So first I'm going to give you a short introduction on biomaterials and biocomposites. Then I will present the numerical model, the validation of this numerical model, then present some simulation results, and end with the conclusion. So biomaterials have been the focus of research in the recent years because they display some mechanical properties that differ from traditional engineering material. So, biomaterial are organized in the hierarchical way, so there is various scale, and at each scale you can find a composite structure of two or more phases, and it's believed that each scale contributes to the optimization of the mechanical properties. So here is an example from a paper by Rich in 2011. So at various scales you can find some various optimization on toughening of the composites, such as crack deflection, fiber and ligament bridging, constrained microcracking, etc., from nano to micro scale. I give there another example of the structure you can find in biocomposites, such as the platelets, oriented platelets, and organic phase of the seashells, the concentric lamellar organization of osteons. The same structure can be observed in the skeleton of a deep sea sponge, and here, mentioned before, the antler osteons with the surrounding matrix. So, these composites are protein matrix, which is tough but not that stiff, reinforced with some mineral phase, which is stiff but not that tough. And you can see that it seems that the biocomposites, such as antler, bone, shell, etc., take the best of the based components. So we believe that the mechanical property is not a simple sum of the base component mechanical properties, but the complex organization is fundamental in determining the functionality. So, to give some evidence of optimization through structure, we developed a numerical model, which is based on so-called lattice models, spring network. So basically, the domain is discretized in a set of nodes. The nodes are connected, bounded in a network. So you can define the stiffness of each bond based on so-called homogenization. So we have the equivalence between the stored strain energy of the continuum and the sum of the stored strain energy of the bonds. So, for example, here is an hexagonal packing where each node is connected to its first neighbors. So there is advantage to use this kind of lattice model because of the discrete formulation, which avoid issues related to singularity when there is a lot of inhomogeneities, such as material inhomogeneity or cracks. So basically, when you have defined your network, you can give some various properties of your bonds to include some line inclusions or domain inclusions, stiff or soft. And then you have to introduce a disorder, which can be a geometric disorder, material disorder, and especially some statistical distribution on the maximum elongation of each bond. It's done by Weibull distribution. You can also have different mechanical behaviors, such as linear elastic or elastoplastic. So we validate this model with the classic continuum theory. So here is a stiff elastic line inclusion in a matrix. You can compare the stress field with the analytic one, which was obtained by Atkinson in 1973. So it's based on the Harris stress function, so there is perfect agreement. We can do the same for the central crack. Here again compared with the Harris stress function from Westgard in 39, perfect agreement. So basically, we take a representative volume element and we apply a step-by-step load, and you can follow the damage formation. So here is an arbitrary scale of damage, which is the number of broken bone in the neighborhood of each node. So basically, the domain accumulates a certain amount of damage until a crack form and propagate, which leads to the failure of the material. So if you take a look at the stress-strain response, you have this quasi-brittle behavior. So it can be described by statistical fracture mechanics. So you can find a nice review of it by this paper from Alaba in 2006. Basically, the tangent elastic modulus decrease while the strain is applied, the damage build, so you can see the stress as a function of the damage level of the material until a critical strain which leads to the failure of the material. So basically the idea is then to add some structure inside with some here stiffener, so some line inclusion which was 100 times stiffer and 100 times more stiff and 100 times less tough. So if you do the same test, you will see that damage accumulates near the tips of the reinforcement and then propagate the crack. So you will have optimization in the strength and in the stiffness with a relatively low loss of toughness. This is because when the damage accumulates in these tips, it will not propagate because it's shielded by the surrounding reinforcement. So this is a very interesting structure. You can do the same with some soft matrix layer. So here the mechanism is a bit different. The damage accumulates, some cracks start to grow, propagate, but they are blocked by these stiff, soft layers, and then more crack will appear, and you have toughening, optimization of the toughness with a relatively low loss of strength and stiffness. So we used this model also to simulate some fiber reinforcement matrix. So we had some random line inclusion in the domain, and we see the influence of the reinforcement on the plastic behavior of the matrix with some comparison with experimental results. So it was some paper by Panzervolta and Wong. And to end, we are perform some ongoing simulation on the self-healing, which is an interesting property of the biomaterials. So biomaterials are able to heal themselves when there is damage occurring. So this is quite early. Basically, we introduce self-healing parameter, which is the number of heal on the number of broken bonds at each step, and we want to see if structure can optimize the self-healing property of those materials. So to conclude, we developed a numerical model that accounts of heterogeneity and fracture nucleation propagation. We compare this model with classical linear elastic theories, and the model is useful to model the mechanical property of composite, and we show that the biological structures can affect and optimize mechanical property, and there is ongoing study on optimal composites and self-healing properties. Thank you very much.